Quick Start Tutorial. Natural and forced convection in a heat exchanger. This heat exchanger model consists of a low-temperature coolant flowing around a series of heated pipes. The multiphysics simulation both involves natural convection, through buoyancy effects, as well as forced convection, by coupling transport of the temperature field with the fluid flow. This tutorial can be run by selecting Model Examples and Tutorials, Quick Start, Heat Exchanger, from the File menu, and followed with the step-by-step instructions in the user's guide. To start a new model, click the New Model toolbar button, or select New Model from the File menu. Select the 2D radio button. Select the Navier-Stokes equations physics mode from the Select Physics drop-down menu. An additional physics mode will be added later to couple and model heat transfer effects. Press OK to finish the physics mode selection. Geometry mode. Only the fluid surrounding the heat exchanger will be modeled. And by using all symmetry planes, the geometry can be simplified to a two-dimensional planar cross-section, which can be constructed by making a rectangle from which a circle is subtracted. To create a rectangle, first click on the Create Square Rectangle toolbar button. Then left-click in the Main Plot Axes window, and hold down the mouse button. Move the mouse pointer to draw the outline of the shape, and release the button to finalize the shape. The geometry object properties must now be edited to set the correct size and position of the rectangle. To do this, click on the rectangle R1 to select it, which also highlights it in red. Then click on the Inspect Edit Selected Geometry Object toolbar button, and change the min and max coordinates of the rectangle, so they span between 0 and 0.0075 in the x direction, and 0 and 0.05 in the y direction. Create a circle, and set its radius and center to 0.003 and 0.02. Select Circle from the Geometry menu. Enter 0.003 into the Radius Edit field. Press OK to finish and close the dialog box. To subtract the circle from the rectangle, first select both geometry objects by clicking on them, so that both are highlighted in red, and then click on the Subtract Geometry Objects button. Alternatively, if the circle is obscured by the rectangle, they can be selected by holding the Control key, while clicking on the labels R1 and C1 in the selection list box, or in this case simply pressing Ctrl A to select all objects. Grid mode. Switch to grid mode by clicking on the corresponding mode toolbar button. The default grid may be too coarse to ensure an accurate solution. Decreasing the grid size and generating a finer grid can resolve curved boundaries better. Enter 0.0005 into the grid size edit field. Press the Generate button to call the automatic grid generation algorithm. Equation mode. Switch to equation mode by clicking on the corresponding mode toolbar button. Equation and material coefficients are specified in equation subdomain mode. In the equation settings dialog box, enter the following coefficients: ρ for the density, μ for the viscosity, and alpha g ρ t minus Tc for the volume and buoyancy force in the y direction. An equation and physics mode for simulation of heat transfer effects must also be added. To access the Multiphysics selection and add another physics mode, press the plus tab and select heat transfer from the Select Physics drop-down menu. Add the selection by pressing the Add Physics button. Note that each physics mode will have its own tab for subdomain and equation settings, as well as boundary conditions. Moreover, FEATool works with any unit system, and it is up to the user to use consistent units for geometry dimensions, material, equation, and boundary coefficients. In the Equation Settings tab for the Heat Transfer Physics mode labeled HT, set the density to ρ, heat capacity to Cp, and thermal conductivity to K. The convective velocities should be coupled from the Navier-Stokes equations physics mode. To do this, enter U and V in the corresponding edit fields, as these are the default names of the dependent variables for the velocities. Press OK to finish with the equation coefficient specifications. The model constants and expressions functionality can be used to define and store convenient expressions which then are available in the point, equation, boundary coefficients and as post-processing expressions. Here it is used to define the material and fluid parameters. Press the Constants toolbar button, or select the corresponding entry from the equation menu, and enter the following variables in the Model Constants and Expressions dialog box. Press Enter after the last expression or use the Add Row button to expand the expression list. Boundary mode. Switch to boundary mode by clicking on the corresponding mode toolbar button. Boundary conditions are defined in boundary mode and describes how the model interacts with the external environment. First, select the tab labeled NS, which allows for specifying boundary conditions for the Navier-Stokes equations physics mode. Then select all vertical boundaries, and choose symmetry slip from the drop-down box. Switch to the heat transfer physics mode by selecting the HT tab, and choose the thermal insulation symmetry boundary condition. Continue with the top boundary, which is the outflow. Select outflow pressure for the Navier-Stokes physics mode, and convective flux outflow for the heat transfer mode. The bottom boundary is the inflow and should be prescribed with the constant velocity v in the y direction, by using the inlet velocity condition. The temperature should here be fixed to the cold low temperature, Tc. Lastly, the boundaries on the cylinder are walls, and should be prescribed with wall no-slip boundary conditions for the velocity. For the temperature, the constant high temperature, Th, should be prescribed. Solve mode. Now that the problem is fully specified, press the Solve Mode toolbar button to switch to Solve Mode. Then press the Tool button, with an =2 sign, to call the solver with the default solver settings. From the visualization of the resulting flow field, one can see that the flow is accelerated when it passes between the cylinders. To show the temperature field, open the Plot Options and Post-Processing Settings dialog box, and select to plot and visualize the temperature, as both surface and contour plots. The temperature plot show that the fluid is heated around the hot cylinder and follows the flow upwards. FEATool also allows for advanced post-processing such as boundary integration. Integrate the expression T minus Tc divided by the width over the outflow boundary to find the change in the mean temperature. Select Boundary Integration from the Post menu. Select 3 in the Boundaries list box. Enter the expression into the Integration Expression Edit field. Press OK or Apply to calculate and show the result of the boundary integration. From the result one can see that the mean temperature along the outflow boundary has risen by about 1.7 degrees. The tutorial is now complete, and the model can be saved as a binary file, exported as a MATLAB M script file, or a GUI playback file.